remind me now. Okay, so any questions about what we went over last time, or any thoughts? All right. So Monica and I got together this morning. I think we finalized on the first project. So she's going to come in around 11:30 or so to go over the first project and the lab report guidelines and that sort of thing. So I'll leave that for her. But just to let you know, the first handout's out here for the photogrammetry lab. This is the lab itself. So you can go ahead and download that. There's some data that you can link to over here that you use inside the laboratory itself. The guidelines and those files that had those links are also right here under the laboratory materials, so you can grab those. For this lab, I don't know if anybody has downloaded Envy yet. Does anybody not? Okay. All right. If you don't have Envy, we're going to need Envy for the first lab to do registration with. And to get there, if you just go to the CIS homepage, and under the About menu here, for some reason, there's a software downloads page. Well, that's up About. But if you click on that, it'll bring you to this page with a bunch of software you can download. So if you're really dying to have signals, that's where it is. Signal show. I don't know if you saw that one. And then NVIDL is right up here at the top. So if you click on the NVIDL label here, it'll take you to a page where you can download it. Put in your RET username and password. Select the version of NV and IDL you'd like to download. I'd recommend NV4.8 with IDL 8.0. That's the latest one. And choose the OS that you have on your machine. You can download any architecture you'd like. And hit the submit button. What that'll do is it'll take you to a page where you can go ahead and download a license file as well as the software itself. Right, so it's pretty big. It's going to be about 300, 400 meg. So that's not too bad to come with the wireless. It'll just take 10 minutes or so. To use it from off campus, if you're on campus, you can use it anywhere. As long as you have the license file installed. But the license file pings back to our license server here in the center and gives you an authentication. If you're off campus and you're not on an RAT network, so if you're in like UC or River Knoll, I think you're still on the RAT network. But if you're in an apartment or a house that isn't on the RAT network, you have to use a VPN client to log in. So the VPN link is right here. This will go off to IPS's page, and you just log in again with your RAT username and password. Download the VPN client. Start that up, start up NV, and everything should work perfect from off campus. So let me go back to where we left off. And we got to a point we had talked about what we thought remote sensing was all about here at RIT. And then we did a little bit of talking about photo interpretation and the way we visually look at photos and understand what we're seeing. And then I mentioned that there was really kind of two sorts of remote sensing that you could do. One where you use aerial imagery to make measurements, and one where you do to make radiometric calls or do analysis based on the digital counts that get recorded. And we're not going to spend a lot of time with the measurement one, but what I'm going to do is go over a little bit of photogrammetry, just so you have a little bit of a background in it. And you'll do a bunch of it in the laboratory assignment that Monica will come talk to you about. I just want to give you a little bit of an introduction to it. So what I did here in the slides was I just copied this right out of John's text. And what I want to do is sort of set a context and put just kind of a common framework about how we're going to use photogrammetry, or at least the notes that will, or the notation that we use in photogrammetry. I think I can draw it out here. maybe not that. All right, well, I'll just use the cursor. So if we think about the ground, all right, and let's say we have an airborne platform of some sort, say an airplane at this point, and we're looking at the ground from straight overhead. All right, so we're going to do what we in remote sensing will typically call a nadir shot. Right, so we're straight overhead. We're looking straight down at the ground. Not looking obliquely off to the side, but just straight down. If we take the center of the optical axis of the imaging system that we're using and project that down to the ground, that's what we will typically label in the scene as the origin. Right? We'll usually use the big letter O to represent that. A lot of photogrammetry texts, what they'll do is they'll use capital letters when they're talking about points that are in the ground plane or the target that you're looking at. All right. So capital O is the origin. That's where the optical axis intersects the ground itself. All right. Now, if you think about the way an optical system will work, is you'll have a lens at this point L. All right. And this is what we usually call the exposure station or the camera position. And you'll get a reversed image on the focal point. All right, so everything will be backwards from the way you're looking at it on the ground. Well, you could think about the world that way, but what photogrammetrists usually do is they sort of turn that focal plane around, they reflect it, and they make a positive of that on the other side of the exposure station. Right? So essentially, if you take this area up here and reproject it down through the exposure station, what you'll have is that same image plane. Right? It'll be on the positive side of the lens. And now the objects on the ground and the objects on that image plane will be in the same positions. Right? So you don't have to deal with that flip of everything. It's really convenient to do that. And what it also does is it kind of sets us up nicely to do photogrammetry in its simplest form with some similar triangles. So if we have our exposure station here, L, and we have our ground plane here, and I project down a line to the ground, and this is where that point hits the ground, capital O, our origin. Right? If I drew the field of view of our imaging system, and say it was that wide, our image plane would normally be up here. But rather than putting up there, what I'm going to do is I'm just going to reflect it through the lens and place it at this location. Right? So now we'll have our origin little o, because we're on the image plane, which will be in the center of that positive rendition of the image that we would normally project onto the focal point. Yeah?
What do you mean? Like that we're going to have a detector?
No. Our detector is always going to be here. Right? So we're always going to form our image at this location. On the other side of the exposure station. All right? So up here, we'd have an origin, I'm going to call it little o prime. Right? All I did here was take that triangle, that film plane or focal plane, and rotated it down below the axis and just placed it right here. This is still our focal length, right? And I'm the same distance away here. So all I'm going to do is reverse it around. The reason I'm doing that is now what I have set up here is a very easy construct to do photogrammetry. And it's just by convention, because now we have similar triangles that we can work with very easily.
So again, you just did the flip.
Right? I just did a flip.
So you didn't avoid the flip, right? But you said that it's more convenient.
Oh, wait, no, I unflipped. All right, so let's say this was a point A over here.
Yeah.
This would be A prime. But this will be A.
After you did the flip in order to get the reverse triangle.
Yes. So rather than having a negative image where everything is backwards after having gone through the optical system, now everything's back in the positions where you think it should be. Okay. So, a couple things to notice. When you measure, when you make measurements with a system like this, you have a lot of things going on, a lot of instruments giving you different values. For instance, if you have a camera flying, you'll usually have a height of the aircraft. Right? When somebody says they're flying at 1,000 feet, what does that mean? not a trick question.
It's 1,000 feet above the ground.
Could be it's 1,000 feet above the ground.
Above that sea level.
Could be above sea level. It could be above what photogrammetrists call datum. Right? So when somebody gives you an aircraft height, you have to ask them, well, what is that above? Right? So in the discussions that we'll have here, we're going to measure aircraft height above what's called datum. Right? Datum is this plane that we have depicted here that's some arbitrary distance below the ground level. Right? What would be really convenient is that this was sea level. But what it actually turns out to be in most photogrammetric terms is the Earth is represented by an ellipsoid. Right? The Earth isn't round, it's slightly ellipsoidal. Nobody's decided on what the right ellipsoid is to represent the Earth. There's many of them. I'd say about 10 different model ellipsoids for the Earth. So now you have to ask the question, all right, you're above datum. That means height above the ellipsoid that's representing the Earth. Well, now you have terrain that varies and goes below the ellipsoid and above the ellipsoid. Right? So the ground, which we depicted here in sort of a natural fashion, is some distance, little h sub a, above the ground at this point A. It'd be little h sub o above datum at this point O. If I had another point, it would be a different height there. Right? So the ground height will vary above datum. So we need to be very careful of that. Does that make sense?
So are you giving the O one when you say h?
Are you given?
Like just like the height at the main point?
Oh, no, see, you really don't have anything, right? You know where the datum is, you know where your aircraft was, and that's all you have, right? The Earth could be any height above that datum, and you don't know what that is. When you do what's called orthorectification, when you take an image and you project it so that everything is square and everything is orthorectified, usually you use a digital elevation model, so a map of the height above the Earth. Right? But then you got to ask, how good is that map? Usually those maps are on 15-meter centers. You have a point every 15 meters or so. So locally, it's not going to be very good, right? So, because you have to interpolate between it. So part of what you can use photogrammetry for is actually to get a very high resolution map of that terrain, or the height above the ground. And that's what we're going to do. Is we're going to try to figure out height above datum and height of objects actually above the ground using just some simple, similar triangle type geometry. All right, so capital H is the height of the flying platform, right? And that's measured relative to datum. I don't know if that's obvious from this illustration here, but that's above datum. So the height of the exposure station above the ground is big H minus little h. That would be the distance above the ground. Okay, so I just want to set the context in this case. Now, one of the things that, well, let me ask you this. If you're going to make a measurement of something in a photograph, right, you can go in and you could measure the number of pixels that something is in the photograph, right? I can go from point A to point B, measure how many pixels distance there are. How do you figure out the physical distance between those 2 points? I have a digital image, I can measure the number of pixels, but how do you figure out that physical distance?
You need some kind of reference.
What's that?
You need some kind of reference to...
If you had something in the scene that you knew the exact size of,
Right.
yeah, you could use that to do a calibration, essentially. Is that going to be good everywhere? No. Why not?
It's calibration per distance.
What's that?
It's a calibration per distance. Like if there is another object that is, I don't know, farther than the other one, so it's different calibration.
So as the ground changes height, the scale in your photograph is going to change. Right? So the scale, we did that with the equation over here. It's a ratio between our focal length, this distance right here, f, which I drew right here. So scale in a photograph is the ratio of f to our flying height above datum. So let me draw datum here. And then a height of our ground above datum. Let's just label that as h generically for right now. So we have f over big H minus little h. Right? That would be this distance right here. Okay, so our scale at this point right here, we can use using that equation. But the scale is going to be different at this point because it's a little bit higher. And the scale is going to be different at this point because it's a little bit lower. So our scale is going to change as a matter of position within the scene. So you got to be careful when you're making a measurement to take that into account. Now, this is sort of relative, and this is something that I'm going to ask you to think about a lot when you're making any sort of measurement. It's relative in the sense that this makes a really big difference if I'm flying very low, right? If F compared to H is, if the difference between those two things is small, or smaller, then this is going to have a more dramatic effect. If I take a imaging platform and bring it to space, put it in a satellite, now all of a sudden a 10-foot change in height on the ground relative to a 420-mile distance that a satellite might be in space, now all of a sudden that's not as big of a difference anymore. So this change in scale across the scene has a little bit less of an effect. You'll hear over time, hey, satellite X, let's say Landsat thematic mapper, that satellite has 30 megapixels on the ground. Right? Well, that's not true all the time. It has 30 megapixels at some particular altitude of the ground. Right? But if you're on the top of a mountain, they're going to be smaller. Right? If you're below the level that satellite altitude is measured relative, it's going to be a little bit bigger. But a lot of people don't ever talk about that because there's such a big difference. But when you're working from an aircraft or from the top of a tower, top of our building here and shooting off, then it's certainly going to have a big difference across the scene. So that's something we need to keep in the back of our mind. All right. So one of the things that you want to do with photogrammetry, one of the simple things that you'd like to do, is be able to take a point on the ground and transform it to a point on your image plane. Right? And these are called the transformation equations. So if I have a point on the ground, point A, which is depicted over here, and I want to figure out the position of that in my image plane, all I really need to do is know where my origin is in both my image plane and on the ground. And then I could measure distances relative to that origin in the x and the y direction, right, until I could plot that point A. Well, those distances are proportional to distances on the ground, and they're proportional through the scale. All right, so what I have over here is the inverse of the scale, because I want to take a image plane coordinate and map it down to the ground. So little x sub A is the position on the film plane, or on the image plane. H is the height above datum again. Little h sub A is the height of the point A above the ground. And F again is the focal length. And then this would be the position of that target on the ground. All right, so I could go from film plane coordinates, little x and little y, to image plane, object plane coordinates, big X and big Y, and be able to map my points down on the ground. So this is how I would go about making measurements. If I had a point, let's say A here, and B over here, I can measure the distance between those two by transforming little x sub A and little y sub A to big X sub A and big Y sub A, ground coordinates. Do the same thing for point B, and now I have positions on the ground, and I can measure the distance between them, right, in ground coordinates. Right? Now, beyond that, beyond making simple linear measurements on the ground, we'd often like to figure out the height of an object. All right, so how tall is something on the ground? And if you look at a photograph like the one down here, let me throw this up. All right, oops. I don't know how well you can see this. We'll just turn the lights down for a second. Okay, so if we're looking at this image, and let's assume I'm shooting straight down. So my camera is located straight overhead, and that if I projected a line down to the earth that was perpendicular to the ellipsoid, I'd be right in the center of the scene. As I look away from that center, I look radially outward in the scene. What's going to happen? Or how am I going to view, let's say, a tree over here? What am I going to see?
You're going to see the trunk, or more than the trunk than, say, just the overhead view of the.
Yeah, if I was straight overhead, I would not see the trunk. If I'm looking at it obliquely, because I have an angular field of view that I'm looking for, I'm going to start to be able to see that trunk. Is the trunk or the top of the tree in the two-dimensional projected image that I have here, which one's going to be closer to the origin?
Trunk.
Trunk. Okay. Because if I draw a line from my exposure station down to the trunk, and I draw one to the top of the tree, the way that I'll project onto the image plane will, in an exaggerated fashion, will look something like this. Okay. All right, so if I know that that's going on, I could go ahead and I could figure out the height of this tree with using a single photograph. Right? So how do you go about doing something like that? Let me just push ahead here. And this is high quality stuff. This is why you pay big bucks to come here. All right. All right. So I just kind of redrew this picture a little bit. So what do I have here? I have my exposure station out, my origin on the ground. I have my tree over here, and I'm going to label the top of the tree point A, the bottom of the tree point B in the ground coordinate system. Right? The image of the bottom of the tree here, little b, the image of the top of the tree here, little a, and I'm going to call that distance from A to B, I'm just going to call that d. Right? I'm going to label the distance from the origin on the image plane out to the top of the tree as r, radial distance away from the center of the origin. Right? And what I want to find is little h sub a. Okay? Now, if you go back to, when did you first see similar triangles? What grade were you in? But this is fun when you go back to your childhood. You see, the older you get, to me, I saw this in 2nd grade. You know, and I know I didn't see it in 2nd grade. I probably saw it in 9th grade or 8th grade or something, 10th grade maybe. But it's fun. The older you get, the longer ago you learn this stuff. It seems like. Right? But you saw it sometime in the end of primary school, beginning of high school. And I could do something really simple here. I could just take some ratios of distances. Right? So let's what I have up top here. I'm going to take the ratio of the distance little r to big R. Well, what is big R? Well, big R is the distance from the origin on the ground out to the projected intersection of the top of that tree with the ground. All right? So if I look at this triangle here, capital L, capital C, capital O. Okay? Big R is this leg of the triangle. if I take the ratio of r, little r, which is the distance out to that point in this triangle, big L, little o, well, that ratio, because these two triangles are similar to one another, well, that's going to equal a lot of other ratios. All right. Well, one of the ratios that it's going to equal is the distance from the point B to point A on the image plane. Right. This distance right here, the distance is right here. Right. Those are also proportional to one another in the same proportion. And we could also look at this leg of this smaller triangle, ABC, and then we could look at COL, and the ratio of little h sub a to big H will be in the same proportion because all these are just similar triangles. Right? So if I set those equal to one another, well, I could do some rearranging, and all I did here was swapped R and BC. Right? I could swap a numerator and denominator, and I still maintain equality, and I could still have it equal over here. What did I want to solve for? I want to solve for h sub a. So let's do that, and let's figure out what we know. Right? Because if we know some things and we can figure out something we don't know, then we're in good shape. So what do I set it equal to here? Well, I can measure little r on the image, right? Distance from the center to that point A. I can measure d from the bottom of the tree to the top of the tree. I know my flying height above the ground. You know, at least if I trust my altimeter in my aircraft, I know my flying height. All right, so I know this, I know this, I know this. I don't know big R. I don't know BC. So I'm not going to use that. Let's cross those out. So let's rearrange this equation here. Little h sub a equals d times h over r, and I got height of my tree.
It's true only if you're assuming that the ground is flat, right?
If the ground is flat next to that tree, absolutely. And where do trees grow typically? In nature. They always seem to be on mountains or hills or something like that. So yeah, you definitely have a problem with that. All right. So, let's see. Another thing, to get a better estimate, and this moves a little bit further towards the kind of things that we do as far as our research goes now, is I can get a better estimate of height. Well, let me ask you this. How do you figure out distances in this room? Right, you look around this room, you know how far, relatively, how far everything is away from you, right? Right, I'm the board, the screen's farther away than I am. Right? How do you know that?
Binocular disparity?
That's a good term. Optical disparity, yeah. All right, that's exactly what's going on. If you have two eyes, they're separated by some distance. You naturally do all the image processing inside to get depth. Well, let's simulate that from an aircraft. Well, more fun. Let's simulate that with a movie. Now we have 3D movies, right? How do those work? Well, you put on glasses, you have an image that's taken from the camera to different locations, and through some filters or polarization filters, you can control which image gets to which eye at a time, and you can simulate that. Right? Well, we've been doing the same thing from aircraft for a long time, where I could have two exposure stations, right, L and L prime, looking at the same point on the ground, and I could figure out how high this little structure is from those two photographs. We're using essentially stereo. All right, now, the technique that we just did using one photograph was called one photo relief displacement. This is going to be called two photo parallax. The method that we're going to use here is a parallax determination. All right, so where does parallax come from? So my plan, or my hope is, that I sort of interfere with the rest of your life in a little bit of a way here. I'm going to make it so you can't enjoy looking out an airplane window any longer, because you're going to just be thinking about too much stuff going on. Now I want to ruin your car trip. All right? All right, so next time you get in a car, look out next time you're riding in a car, not while you're driving. Look out the side window and stare out the side window for a while. Okay? And you may have done this already, but if you look at objects in the distance and you look at objects close to you, is there something different between what's happening to your apparent vision?
This is the things closer and moving much faster than things further away.
Yeah, the things close to you seem to be moving much faster than things farther away. Are they? Not really, right? It's just an appearance because they're closer to you. The scale's different. The same change in distance is going to result in a larger physical change in the position on your focal plane. Okay. That's all that's going on. And we're going to rely on that same fact here. The top of this tower is going to move less than the bottom of the tower between two photographs because it's closer. Oh, wait. No, it's going to move further. Sorry. The top is going to move further on the two photographs than the bottom.
So you don't have two sensors, you're just waiting a little bit of time and taking another picture?
You do it any way you want. You could have two sensors, or you could just fly a plane. Take a picture here, a little later on, take a picture over there. But either way would work. You could do it from two sensors. Right now, a lot of the research that we're doing it from multi-sensors. So we have 50 sensors looking at a building, and we can get the positions of all the points in three-dimensional space. But this is the way you start out, two at a time. All right, now, what you can go ahead and do, I think I like, ooh, here's another relief displacement one. All right, so you can do it with those similar triangles and the proportions, or here's another way you can go ahead and derive the same equation we came up with, but I actually drew the tree here. I got it pretty artistic. I'm pretty proud of that. All right, so let me go on to the next one. All right, so let's just simplify that illustration in the book for a second. I have two positions, L and L prime, like I said, two camera positions. I have my tower. Top of the tower is A, bottom of the tower is C. Right? I have my ground plane. I have my datum plane. I have my height of point C above the ground. I have my height of point A above the ground. The scale is different at those 2 points. And so you got to remember that if you're trying to find the position of A and the position of C in the ground plane, you can't use the same scale because the scale changes. And flying height above datum is H. All right, C and A are the projections of big C and big A onto the film plane in this exposure. C prime and A prime are the projections on this exposure. Right? Check out what happened here. In this photograph, C was closer to the origin than A. In this photograph, C is also closer to the origin than A. Right? And that's the way it should be. But on the photographs, they actually reverse the positions because you're looking at it from a different angle. It's all going to fall out in the wash because if this is the origin, these will be positive measurements to this side. These will be negative to this side. Right? So you want to maintain sign when you're making measurements on your photograph. Everything should be relative to the origin. All right, now, to go ahead and solve for this, the little trick. Let me try and draw this. Smaller window here. Okay, if I go ahead and I take these two geometries that I have here, and I redraw them so that I make the exposure plane, or the exposure positions, L and L prime coincide with one another. What I want to do is I want to put L here, right? And I have my image plane here, and I have my projection down to A, and my projection down to C. So here's little a and little c. All right. If I go ahead and I take this exposure station L prime and shift it back this way, so it coincides with L. Right? Essentially what I can do is then draw my two projected points down to A and C again. here's my tree, and here's my tree, and all I've done is I've just shifted these together. Why did I do that? Well, if I continue and finish out this triangle, now I have a bunch of similar triangles that I can work with. Okay? They're not two separate stations any longer. Right? As long as the camera looks straight down in both positions, I can do this. I can shift one of them over here, and now I have, what do I have? I have A prime out here, and C prime over here. And now I can start to make those measurements that we just talked about. When something was closer to me, you said it moved faster than when it was further away. Well, you could measure the distance between these 2 points. You can measure the distance between these 2 points. All right? And now you can see that A, because it's closer to you, moved further on the image plane than C did, because they're farther apart from you. Right? So that's the parallax. Right? And that's the measurement we're actually going to make. We're going to make the measurement of how far does A move in the image compared to how far does C move in the image. If I know that relative distance between the two of them, then I can go ahead and derive the height above the ground. All right, so can't show both of these at the same time, unfortunately. No, I don't think I can. All right, so essentially here's what we're going to go ahead and do. One of the key measurements that you make when you do a parallax measurement is you need to know how far your aircraft moved. Right? And if we go back to this illustration for a second, the aircraft moved from L to L prime. We're going to label that as B. Normally that's what's called the baseline of the set of stereo photographs. How far apart the two cameras were in a stereo situation, normally referred to as the baseline. And so that's why it's labeled B. All right, so I can look at some ratios now. All right, I could do the scale. Here's the inverse of the scale, h minus h sub a over f. Right? And I'm going to equate that to the baseline over the distance that at point A actually moved on the image plane. Right? Little x of a minus x prime sub a. Right? And this is just in the x direction. Right, so if we go back and let me just write that down here for a sec. H minus h sub a over f equals b over little x sub a minus x prime sub a. Just so we have that. All right, so what did I say there? Well, I said the ratio of this distance, right, which in a triangle is what? This distance here, right? Base of the triangle. Okay. So the ratio of the base of the triangle to the height of the triangle. So here's the height above the ground, here's the base above the ground. Those two things are proportional to one another. Well, they're in proportion to they're the same as f, focal length here, and the distance between the x positions of point A and A prime. All right, so this distance to this distance is proportional to this distance to that distance. So that's all I need to know, right? And from that point, I just do some rearranging, and I wind up with my parallax equation down here, where the height of the object is the height above the ground minus the ratio of the baseline, the distance between the two exposure stations, times the focal length, over the parallax. Right? The parallax is what we define x sub a minus x prime sub a to be. And how far does an object move on your focal plane when you go between two exposure stations? Yeah?
Can you go back to the diagram again?
Yep, this one?
No, the one you drew.
This one?
That one.
Okay.
So you said it was the base of the triangle, isn't it? Just from C to C?
Yeah,
Ooh,
things like
yeah.
that.
This one here, you're saying, right?
Yep. Which is the same as from A.
Yeah. That's, I was looking at the wrong triangle. Yes, Yeah, you're absolutely right. So it's this triangle, this inner triangle. Yep, sorry about that. Right, again,
But do you,
things need to be the same height. I mean, you have a lot of criteria, a lot of
Yeah,
assumptions
yeah,
that
Is
go
that
into
CBC
it.
then? Like lowercase c?
What's that? I'm sorry.
I don't think it's A to A then, isn't it C to C for the little one?
It's
Like
well,
C.
it's A to A for one and C to C for the other. So
Oh.
the base changes.
but the base is the same
Oh,
because
what?
you're assuming that both the object is supposed to be just vertical. So the triangle, the base of the triangle just moves up and it's the same distance.
That's right. So here's when you're looking C to C, it's this triangle. Because this is really helping, right? Let's see. Oh, cool. Crayons. That's awesome. All right. So when you're looking A to A, no, I apologize. When you're looking C to C, it's the red triangle. When you're looking A to A, it's the green triangle.
I see what you're saying.
All right. So then B is the same in both cases.
Okay.
Make sense?
Mhm.
All right.
But it's not true actually.
So that's what's called height determination from parallax. Now imagine you have two stereo photos. If you went ahead and did every pixel in the scene, right? It's not an easy thing to do, but if you could do every pixel in the scene, what would you wind up with? Well, you'd wind up with all these heights, and that would be a height map of the ground above data. Right? So you could produce a three-dimensional map of the ground. Sounds easy, but you got to pick matching pixels on both scenes. Right? It's easy to pick the top of the tree and the bottom of the tree. How about if you have a grassy field? How do you pick the same blade of grass in one as you do in the other? That becomes a much harder problem. So in order to get partially the way there, what you could do is you can register two images to one another. And you can make one image fall on top of another image through some sort of a mapping transformation to make that happen. Now, we're going to go over that in detail, how to do that in image processing class. Okay? And you all should go through and write the codes to go ahead and do that affine transformation. Is anybody in the multi-view class right now? Somebody taking that as an elective? Okay, you can see it again there. But there, we're going to do it with a different methodology. By what's called finding homography between two image sets to come up with three-dimensional data. And that's what's called dense point cloud construction. So you'll see that there. So for now, what I want you to do this registration, and Monica will talk a little bit about this, is we're going to use NV to actually do the image-to-image registration. Just so you can go through that process, see how it's done. And then we'll look at the details of that next quarter image processing class. All right. Make sense? Feel like full-blown certified photogrammetrists? Okay. That's where I want to stop with photogrammetry. And that's you'll have a lot of practice with this in the lab. Be able to do some of this sort of thing. Now, one of the things you obviously want to always do when you make measurements is come up with an error. Right? I can come up with the height of that tree, but how good is it? You know, I'd say it's 10 feet, plus or minus 5 feet. Is it plus or minus an inch? Is it plus or minus a millimeter? You know, to be able to come up with that error is very important. So, if you know or can predict some of the errors that you might have in each one of these measurements, what's my error in my flying height? Right? What's the error in the focal determination for my lens? What's the error in my measurements on my image plane? Right? I'm counting pixels. Right? Well, pixels are integrated areas on the ground. right? We always think of pixels as being the center of the point that we're at. Well, the center of one pixel to the center of another pixel is a finite distance. So if I'm measuring something in units of pixels, I have an inherent error built right in. Okay? So you have to look at all those errors and go through an error analysis on this data to come up with an error on your final measurement in relation to that. Has anybody ever done what's called there was a book came out in the 1950s. It's a little tiny book, it's about 30 pages long, by Y.A. Beers, that went through error propagation using partial derivatives. Has anybody ever done a partial derivative error analysis? All right. Well, you're going to do a partial derivative error analysis for this lab, right? And there's a write-up in the book on how to do that. But you can imagine if you could take this equation that you wind up with here, right? This measurement h sub a is going to be sensitive to each of the parameters on the right-hand side, right? It's going to be sensitive to how well I know focal length. And it's going to be sensitive to how well I know the baseline, and how well I can measure my parallax, and how well I know the flying height. Right? Any error in any of those is going to give me an error over here. But an error in focal length might give me less error or more error than an error in flying height, depending on the way this equation's arranged. Right? So that's where the partial derivatives come in. If you can take the partial derivative of your independent variable with respect to each of your dependent variables over here, I'm sorry, your dependent variable with respect to your independent variables on the right-hand side, you can assess that sensitivity, because essentially what is the derivative? It's the slope, right, between those 2 points. So the steeper the slope, the more sensitive your dependent variable is going to be to an error in that independent variable. So it's a very, very straightforward method. You should definitely read it. If you can find a copy of this book that was published in the 1950s, it's an awesome book to have. I don't have one because I've never been able to find it. But Schott has one up on his shelf. He doesn't let it out of there. I think he has a lock on it. But it's a great little text. But he's done a really nice summary in the text, so you can walk through that real quick if you got to do that. All right. Any questions from photogrammetry side? All right. So let's take a real quick look at just a couple more concepts before we move on and start talking about radiometry. All right. Remote sensing and photogrammetry all started with film, right? Started back, really heavily, probably in the 1950s, 1960s, when we really started to use photogrammetry from remote sensing data. And there was definitely problems with film. Well, there was great things and bad things about film. Right? Film was wonderful as far as resolution goes. You give me any digital camera that you have today, and you give me a piece of film, and the film's still going to have better resolution than any digital camera that's on the market still. Right? That's great. That's a good thing. What does that let me do? It lets me gain finer measurements. Right? My parallax I can measure much better on film than I can on a digital image, because I have more resolution. I can see finer details. Right? But it had a problem. Think about measuring on a piece of film. This is something you might not think about very often, because you probably, has anybody ever touched a piece of film? All right, a couple of you. This is getting scarier. But imagine you've seen film, right, in a history book somewhere. All right, you have a negative, let's say. It was a piece of acetate, right? It's a plastic polymer material that had an emulsion, chemical emulsion coated on the surface. You take that piece of film, you put it in a camera, you expose it, you take it out of there in the dark, you put it in a bunch of chemicals, you slosh it around, and you take it out, and you dry it, and then you look at it. All right, it's a polymer material. What happens to materials when they get wet? If you got a piece of paper wet, what happens to it? Expands, wrinkles, all kind of stuff happens. Right? If you get a piece of film wet, same things happen. It stretches. It changes shape. So what we all did just now was assume that everything was where it was on the film when I took the picture. But in fact, after you develop it, it probably moved a little bit. So you're going to have some errors because the film changed. All right, so digital cameras come along. Focal planes on digital cameras don't change dimensionality, do they? Yeah, they do. Right, so we still have the same problems there. Right? We have camera distortions. Lenses don't focus everything the same at all different points. So we have focus distortions. We have geometric distortions. If you took a picture of a grid, a piece of graph paper, you're not going to have perfectly straight lines everywhere. You're going to have distortions. So we got a problem there. We had that problem on film too. So that didn't go away. So there's always problems with whatever imaging system we do when we're trying to make measurements. And the thing is to characterize those. We actually have a cage over in building 17 that's meant for geometric calibration of cameras. So if you ever do in your research need to have a calibrated, when I say calibrated in this sense, I mean spatially calibrated camera system, we can give you a camera model that will move every point back to where it should have been before the optical distortions went in place. So we have one of those cages over here. All right, so good things and bad things about both of the systems. But I got to say, there's not a lot of downside about electro-optical systems. Right? And what really drove the development of electro-optical systems was the military originally, right, to do reconnaissance. And where did it really start to get driven? Well, film was great, but it worked in the visible wavelength spectrum. And it worked a little bit in the infrared, with color infrared film. And then we were done. Right? Because we didn't have film that was sensitive to the SWIR, or the mid-wave IR, the long-wave IR. So there, we began to make other detector materials, which required us to go and create electro-optical systems to do that. So if you look back through history, thermal infrared was really the first place where electro-optical systems were used to image not reflected photons from the ground, but self-emitted photons from the targets that we're looking at. So this photograph over here, we saw a couple of thermal infrared images the other day, but this one is a power plant that's pouring its hot wastewater out into a lake. Okay? So you can see it took cold water in. I think the cold water intake here was on this side of this little abutment of the land. So it pulled in cold water over here, cooled off the turbines, ejected hot water out into the lake. But it's kind of neat where you can start to see the distribution of temperatures in that lake. You couldn't do that with film, unfortunately. All right, so electro-optical systems really got driven by this, but then we came up with all kinds of different detector materials, and we were able to see in all the different wavelength regions that we can see today. This is an image from our WASP sensor. All right, our WASP sensor that we fly here, WASP stands for Wildfire Airborne Sensing Platform. It was built to do wildfire detections. We now use it to fly everything that we do here in the lab. So if you do need imagery at any point during your research, we have a system that has an RGB high-resolution camera on it, along with a shortwave infrared, a midwave infrared thermal, and longwave infrared thermal camera. Right? What you're looking at here is a burning forest fire. And if you look in the RGB and you imagine flying over a forest fire, what do you see? You see the smoke. Right? That's what you're seeing here. That's all you got. If you look in the long-wave infrared, you can start to see the temperature distribution on the ground. Right? The scattering that's caused by the smoke in the visible wavelength regions has very little effect on the long-wave region, so you can almost see right through the smoke. But what you're seeing here is heat. You're not seeing fire, you're just seeing temperature. Right? So things that have recently burned are still hot. So these aren't necessarily fires that you see, these are just warm areas on the ground. Midwave infrared is the same sort of phenomenology. This band right here is the shortwave infrared. This particular band on WASP is at 1.7 microns. Turns out that 1.7 microns is the middle of an emission line for potassium. I think I mentioned this the other day, but all burning material, leaf litter and shrubs and anything biological that has potassium in it, and that's trees, all kinds of shrubberies, when they burn, they give a really high emission right at that 1.7 micron band. So it also turns out that you can see right through smoke because there's no scattering at 1.7 microns, or very little scattering. So what you're seeing here on the ground is actually burning biological fuels, right? So leaves and trees and cellulose at this point. Right? So these are actual fire fronts compared to what you're seeing down here, which is just warm areas. So this is kind of neat because we can see the fire fronts on the ground and direct the firefighters in real time right to those locations. We fly over a lot of the Midwest forest fires when they burn every year with our WASP sensor, and in real time can radio down imagery with maps and get people on the ground, firefighters, to the fire front safely, as safely as possible. So that's kind of a neat system that's come about. All right, now, back in the 1960s, we had the whole Cold War thing going on, and the space race was going on, and really cool science was happening, right? Because everybody was afraid of each other, and they just drove the scientific communities to develop more and more exotic sensors to see what was going on, over the fence. And one of the systems that's been recently declassified, it's been classified for probably maybe 10 years now, was one of the first satellites that the U.S. intelligence communities put up, which was called the Corona satellite. These are photographs from space aboard a satellite taken on film. So you think about that for a second. Got a satellite, I got film in it, and it's taking pictures. How do I see those pictures?
You get another plane to pick up the film.
Yeah. Right? So if I was to go out today and start a project, and somebody told me, you know what, put up a satellite, put a camera in there, put some film in it, and then have that satellite eject the film and catch it and bring it down to the ground and process it, I would look at them and say, you are nuts, right? But in the 1960s, it was wonderful. There was 1,000 people that ran out and did this. And I don't know if this will work. There's just a little video of the capture system here. Oh no. Yeah. Well, that stinks. Where'd that go?
Did you ever meet Kurt Winnijika?
Oh yeah.
His dad actually flew the last mission that did this.
He was the pilot on the last mission?
Isn't that awesome?
It is very awesome.
I don't know if he was the pilot or if he was on it, but that was his group, and their group had the little patch that said to catch a falling star, and it's actually what it meant, because they were catching the cancer.
It's not a text, maybe it's image.
Yeah. What do I want to do?
You probably just have to type it.
Wow. All right. One more time. All right. Why don't we take a break? And I'll have this up when you come back. But it's kind of cool. All right, so imagine it's 1960, you went into the theater, you're all sitting there, the theater's filled with smoke because you can smoke in the theater. You have the 3D glasses on, and then this comes out.
Air Force flying boxcars deploy over the Pacific Ocean target area of the Discoverer 14 nose cone capsule, which is snared in mid-flight as it plummets to Earth from orbit. The mid-air recovery at 10,000 feet is the second recovery of a man-made object from orbit. Shortly afterwards, Russia announced the third successful re-entry of a nose cone carrying 2 dogs and some rats and mice. Dramatic strides by both sides in the space race give promise of major developments in man's efforts to actually send human explorers into the far reaches of the solar system. America's Man in Space and satellite research programs mark continued a significant achievement, exemplified by a sky now filled with American moons.
All right, so Yeah, it was the nose cone of us. Right? No, that was a film canister filled with film coming off Discovery 14, which was the Corona satellite. That was the public name of the satellite at the time. Kind of indicates how many failures there might have been before that. But each mission had a subsequent number, so I think this was the 14th recovery. So this capsule that comes down, it's actually on display down at the Smithsonian Air and Space Museum in Washington right now. Maria was saying this, that what happened if we missed this thing? Right? You had a roll, it probably had several thousand images on it. Usually the missions were on the order of 20 days or so long, and then they would eject it, and you get the data back. You could get it back quicker if you wanted to, but most of them went about 20 days. And if they missed this thing, and somebody else got a hold of it, well, it's photographic film, there was no digital encryption, there was no any way to protect the data, you just had to go develop the film. And what would happen if somebody else got their hands on it? So what happened was they always did this so that the ejection, if it missed, would fall in the ocean, right? But then you could send divers down and recover that. Well, what they did on the side of this was put a little plug that was made out of salt. So it was sealed, but the minute it hit ocean water, the plug dissolved. It flooded the inside of the canister with salt water, and the film was specially designed by a company that makes film. I won't go any further. And it would wipe the latent image away off the film. So it would actually destroy it if it did come down. At least that's what we were told. So kind of a very cool system. But you got to go see this thing. If you're ever down in Washington, D.C., stop by. The entire satellite is there, cut down the side. It's probably a replica, I'm assuming. Or it might have been one that never got launched. But you can see the film transport mechanism inside, the ejection mechanism. It's really kind of neat. They have a whole bunch of the videos playing in the cover. All right. So, come on. There you go. All right, so that's some of the first stuff that came down and needs to be classified. There's other stuff that's been declassified since from some of the electro-optical systems too. If you go out to the USGS website, you can get archives of old spy satellite imagery. Kind of neat stuff. All right, and then all of a sudden, we decided that digital systems might be better. We could actually use telemetry to get that data down to the ground. You don't have to recover a film canister. So this is digital concepts. This is a very informative slide. There's digital counts that make up digital images. You probably knew that, right? Okay. So we'll look at everything that we'll be working with here at this point will be digital. The lab that you're going to be working on, the photogrammetry lab, is actually scanned film. All right. So we took the film and we scanned it, so you have digital images to work with, but the actual image data itself was collected on film, actually over Syracuse University, like 20 years ago or so. It was fun. I got my lab notebook out the other day from 1985, and I did exactly the same lab that you're going to do right now, only I did it on film. I was just flipping through it, I'm like, wow, that hasn't changed in a long time. Same images. All right. So, what I want to do now is start to look a little bit at how we're going to use remote sensing data as an image processing, or I'm sorry, a radiometric image analysis system. Right? So we just did a couple measurements doing photogrammetry. We now know how some of the systems evolved. But now let's start to take a look at radiometry. Now I'm not going to cover the radiometry because I'm assuming you all did that last quarter. And what I want to do now is actually start to put everything you learned last quarter to very good use. Okay? And we're going to look at this in two different ways. The energy that's reaching our sensor comes from primarily two different sources. Right? One of the sources of photons that reach your sensor are, we'll call them solar photons. Right? The sun's up there, shines on the Earth, reflects off the targets, goes back up to the sensor. And then there's the self-emitted photons. photons. Those are the photons that an object, because of its temperature, emit on its own. Right? That's really the two sources of photons that we're going to focus primarily on in this class. Right. Now, it's not a hard concept at all, how all this works. But the minute you start thinking about it, you start to believe that there's no way that I'm ever going to solve this problem. All right? And I want to give you sort of a sense of this in a very intuitive fashion, because I want you to be able to sit down and derive from scratch what we're going to call our governing radiance equation. Right? You'll hear lots of talks from folks doing research in the lab right now. People refer to the big equation all the time. Right? At one point in time, we called this thing the big equation, and it's sort of stuck. It's just because there's a lot of terms in it. Right? But it's the governing radiance equation that we're going to derive. And I really want you to never have to memorize the thing, because I want you to be able to just think through the problem and be able to write every single term in that equation. And it's a very easy thing to do in the end if you just go through this kind of thought process. All right, so let's start by just looking at this particular illustration right here. So we have the sun sitting up here, and we have a sensor sitting over here, and we have a set of targets down in the right. Okay? Now, there's a lot of photons that reach that sensor, right, that come from lots of different locations or from different sources. And I want to trace those paths so we understand where each of those photons is coming from. So if we have our sun sitting up here, let's start at the beginning of the alphabet here, and we'll look at path A first. Right? I have photons that leave the sun, go down to the earth, strike my target, reflect it from my target, and go up to my sensor. Right? That's the most natural set of photons that you can ever imagine. Right? Source, target, sensor, photons go and reflect and go directly to the sensor themselves. We'll call those directly reflected photons. Okay. And that's path A. All right, now, the next path that's sort of interesting is path B, right? Where I have photons that leave the sun, come out in a direction, get scattered by the atmosphere, right? Some of those scattered photons fall onto my target of interest, get reflected from my target of interest up to my sensor. All right, that may be not as intuitive, but it's something you encounter all the time. If it's a nice, clear, sunny day, like I think it is outside today, go outside, go into the sun, and you'll have solar photons coming down and hitting you. Right? You can see things are reflecting light, that's all great. It's all working exactly the way we think it's going to. Now walk into a shadow. There's no solar photons hitting you any longer, right? Directly from the sun, but you can still see, right? You can still see things around you. There's still light falling on you. There's still light falling on all the objects around you. But those are the photons that we're calling type B here, that are scattered by the atmosphere and then come into the shadow and allow you to be able to see inside the shadow. Okay. So that's your B type photons, scattered photons coming down to the target, up to the sensor. All right, C, right? C type photons. If photons are getting scattered here, well, they're getting scattered here, they're getting scattered here, they're getting scattered everywhere. They're getting scattered here. Some of those scattered photons will just go directly to your sensor. That is usually what we call sky shine. Right? These are photons in the air that never hit a target, never make it to the ground, but get scattered and go directly to your sensor. As we go on to develop this equation, the sort of radiance that you get from those types of photons is usually what we refer to as an upwell radiance. So it's upwell from the sky, or the intermediate intermedia between you and the ground. All right. So if you're, this is where I'm going to ruin the airplane ride for you. So next time you're in an airplane and you're flying somewhere, you know how you fly up and you can see the ground, you know, you're just leaving the ground at the airport, everything's nice and crystal clear, and you go up a little bit further, and what happens? It's not quite crystal clear anymore. Why is the ground not as clear as it was? that silly atmosphere between you and the ground, right? You got all this scattering material that's between you and the ground. So as you go up and you get more atmosphere between you and the target, the ground, at that particular location, the number of C-type photons that reach the sensor increases. The more atmosphere you have, the more C-type photons, the more scattering that's going to occur between you and the ground. Okay? So if I'm looking at reflected photons from the ground, from the A path, and that gives me a signal, and then I look at photons from the C path, and that gives me some signal. If the C path increases, right, because I'm higher, what happens to my A path if I go higher? Does it change?
Decrease.
Decrease? How come?
Because there are also scattering in this direction when it goes to the detector.
Absolutely. So as A starts to come up, you lose photons because of scattering out of that path. You gain some photons back, right, from the area around it, that's C. Right? You also lose some photons because of transmission effects too. Just so absorption. So you have both scattering and absorption going on at the same time. So as you get higher and higher, if the C-type photons are increasing and the A-type photons are decreasing, what happens to the contrast of targets on the ground? It decreases, right? Because you have this additive term that you're adding in on top of it. So if you had a 10% reflector and a 20% reflector next to one another, you know, if you were right at the ground level, you'd probably have a 2-to-1 ratio of photons getting to you from both of those. But if you add in some C-type photons, that ratio is going to decrease down to 1.5 to 1, 1.3 to 1. You know, hopefully not down to 1 to 1. Well, does it go down to 1 to 1 at some point? You ever go outside and it's so foggy you can't see across the street? That's a situation where it goes down to 1 to 1. You don't have any contrast any longer because all you're seeing is C-type photons. All right. So let's go back into the airplane. Right, now you go above, you go through the clouds, you're above the clouds. You're flying along, and you have a broken cloud sort of situation. So next time you got to look at this. Because if you're flying along, and you look down at the ground, and then you look in two directions. Down at the ground, where the sunlight's hitting the ground, in a broken cloud situation. Right? So that's a picture here. All right, so you're here in your airplane. You got a cloud here, and you got a cloud over here, and let's say your sun is here. And here's your ground. If I look down here, all right. That's in the shadow. So let's project the shadow of the cloud. Of the ground, right, so we got that big old shadow of the ground. If I look here, and then I look over here, all right, I have area in sunlight and an area in shadow of the cloud. What's going to be the difference between those two? Or maybe you've seen this. Have you ever looked outside and said, hey, I'm looking in the cloud shadow, I'm looking in the sunlit area? You ever notice the difference? Where's there going to be more scattered photons coming from? Sun? Well, on diagonal when you're in the sunshine, right? Because you have to have your atmosphere here, right, is scattering light. Here, there's no direct sunlight, so there's no scattering, or very little scattering going on, because there's less photons coming directly from the sun. So when you look in this area, this cloud covered area, you're actually going to be able to see to the ground much more clearly. The contrast of the two objects on the ground will appear higher under clouds than when it's in a sunlit area. So you got to look at that next time. And that's all I see now when I look at an aircraft. I just look at that all the time. And it's really, you know, it's right there. And that's the sort of intuition that I want you to develop as we go through and look at this stuff. I want you to think about, you know, where are the photons coming from, where are they going to, and what path did they take to get there. And if you can do that, then this whole concept of radiation propagation in a remote sensing sense becomes a very easy task for you. All right, so that's A, B, and C. Now, let's look at, let's skip a couple letters and look at G, I, and J. All right, we'll look at the other ones a little bit later. They come from different sources. All right, so let's first look at the I-type photons. All right, so we have the sun, illuminates the ground over here. When you hit a target on the ground, you think of reflection as happening in the opposite direction of illumination, right? But it also happens in all directions, right? You learned about scattering, right? Objects scatter in all directions. So some of the light some of the photons are going to come right back along a path. Some of those are going to go directly into the sensor. Some of them are going to scatter again in the atmosphere and get directed towards the sensor. Right? So imagine the I-type photon here, as you come down, you hit the ground, some of them get reflected back in this direction because of the scattering phase function. Hit another object in the atmosphere, gets scattered in the direction of our sensor. We have photons coming that way. These kind of photons are actually very problematic when we're trying to do radiometry. Right? Because imagine what's going to happen here. Let's say the top of this building was white. Right? It was a green building. They put a white surface on the top to keep heat absorption from coming in. Let's say this is grass over here. So if my target was the top of this building, I would get white photons coming up to my sensor. If this was grass, what color photons am I going to get scattered? Let's assume it's summer and lots of water, you know, green grass. So you're going to get green photons coming back this way. Right? Now, you might say this is a non-selective scatterer, so the scattering should be spectrally uniform. Well, that's true, except that I only have green photons coming back here. Right? So the only thing that's going to get scattered is green photons, so I'm going to get some green photons back to the sensor. So what's going to happen to the color of that roof?
Green.
It's going to look a little green. And it's not because the roof is green, it's because some pixel or some photons from an adjacent object got scattered back into my path into my sensor. Right? And this is what's referred to as an adjacency effect. Okay? A material adjacent to the object that you're looking at reflects photons, they come on back, they scatter back into your line of sight to your target. Right? And they'll tend to color the target itself. That make sense? All right, so let's look at one of the others. G-type photons. They come down from the sun. Let's say our target right now is this little area next to the building. G-type photons come down, reflect off the building, reflect off the target, go back up to the sensor themselves. So now, what have you done? Well, you've illuminated your target with photons from another object in the scene. So we call these background photons. So this is a background object compared to the target that you're looking at. All right, now, this works really well. Anybody? You have a white shirt on, right? So you're probably the only one that can see this today. But you know, go outside afterwards, and it's still morning, so the sun should still be on that side. Take off your coat, look at your shirt, okay? And walk outside next to this building. This building has these big rose-colored glass windows that reflect a lot of light, and the reddish brick. Right? Let's say that's our building. White photons come down, get reflected, brick color and rose color, fall onto your white shirt. Now your white shirt tends to look a little pinkish, a little reddish. If you don't adapt, your eyes are going to adapt and it's going to look white very quickly again. But if you actually took a radiometer, spectral radiometer, and you measured the shirt, your shirt would no longer appear white when you're standing next to this building and you have photons from the building coming onto your shirt. You're actually going to see a little red rise in your radiometric spectrum. So these background pixels, or I'm sorry, these background photons can color an object just the same way as an adjacency effect can. What do we got left here? We got J-type photons. All right. Light comes down, reflected from your target, go up, get scattered by the atmosphere, come back down onto your target, and then go back up to your sensor. So what's happening here? Well, you have a coloring or a spectral change in the photons once they reflect. You get another spectral change from the scatterer that's in the atmosphere. You know, it depends on the wavelength. It'll be scattered differently depending on the wavelength, but you can get a color change again. Comes back down, reflects, might be off a totally different target. Right? This might have been the sidewalk, this might be grass. So this one path can go from sidewalk up, get scattered, come back down, hit grass, go back up to your sensor. Right? But you previously colored your photon. This J-type photon here is no longer white, it's the color of the sidewalk. Gets scattered, could get colored there due to the scattering, comes back down, gets colored off the target you're looking at, and then goes back up. And you can imagine that could happen an infinite number of times. Right? It could just go down, get scattered, back down, get scattered, back down, get scattered. Eventually you don't have enough photons to see, right? Because most things in the world are 10% reflectors, 20% reflectors. So a couple of these reflections, all of a sudden you have no photons left. So it starts to become negligible. But to some point it's very clear. All right, so to illustrate this, this is grass. This is a black painted board and a white painted board. Okay? So if I have light falling on this white painted board, and then it comes down to the grass, and it gets reflected to my camera, right? Those are colored one way. These are colored another way off the black section. But do you see any difference in the grass? Does the grass look fairly uniform across there? Yeah, I mean, this is pretty uniform. You don't see any effect. The reason you don't see any effect is what kind of a scatterer is grass? Inversion, right? So you don't get a lot of photons directly towards your sensor from the grass. You just get a couple. And it's fairly low reflectance to begin with, so you don't get a lot of photons. If you look very, very closely, it would be a little brighter here than it would be over here, but it's hard to see. So in this sort of a case, it's negligible. All right, now this is the trunk of a car, right? A painted trunk of a car. You see the reflection there, right? These are white photons, or photons that come from the sun, go off a very specular target, in this case, and then back towards the sensor, right? So the scattering properties of the material next to the building is very important. What's also very important is the reflectance, right? This is a black car, you see that reflectance off of there. What if it's a white car? Then the directly reflected photons are going to dominate the background reflected photons. They're still going to be the same number, right? But because this car is black, the number of photons that get reflected from the black car is low. So the background ones are significant. If this car was white, then the number of photons that get reflected from the car directly from the sun is high, and the number of photons that get reflected from the background is negligible. And so you got to keep that in mind all the time when you're looking at anything. Right, so do you see why I'm saying this is kind of an impossible science to do? Right? Well, it's very possible. You just got to keep all these things in your head all the time and be thinking about it. All right. So, any questions? All right, we'll get deeper into the solar photons on next Tuesday. We'll talk about lab.
Yeah.
All right.
Be over there
for the microphone, yeah. Like my pictures?
Oh yeah. Electricity value there.
You know it.
Okay. Hi everyone, I'm Monica. I think I've probably met most of you like at some point last quarter and stuff, but if you haven't met me, if you haven't been in my office, I sit up on the 3rd floor in 3206, so kind of the back hallway. There's a whole bunch of like grad student offices in there, so I'm kind of to the back left. You can come in and find me. So the first lab's been posted. I think it's going to be due right before break. Bad for you guys because you have to do it now, but good for you guys because then you don't have to worry about it on the break. If you already went on and grabbed it, go on again because it's different. It's new now, and then the images have also been put up there. So there's kind of 3 parts to the first lab. There's a photogrammetry component, so you're going to be determining the heights of some different objects using parallax and wave displacement and all that good stuff. And then there's an error propagation component and there's a registration component. So the page numbers where all those things are in the book are also in the lab handout, so you're going to have to go in the book and read about it and kind of figure out the equations and stuff like that. So you're going to have to do a little bit of research, but it's all pointed out where you need to do that in the book. I know last quarter for programming, some people use IDL, some people use NV or MATLAB and stuff like that. That's fine. There's not a lot of like programming for the labs this quarter, but you do have to use NV. So if you don't have NV already, you can get it. So you can either use it on the machines that are here in the center, or if you go to the CIS website, there's something called About in the upper left corner.
I showed them that.
Oh, you already showed them?
Yep.
Oh, okay, sweet. I'll set that. So yeah, so that's the first lab. Honestly, when I did it, it took me a little while reading through the book, figuring out the equations, like figuring out how to use the images and stuff like that. So I would definitely suggest getting started on that soon. And so just a couple things about the lab reports. There's also the guidelines posted. You can see them there, guidelines for the lab report material. And a little bit different. So I know last quarter, like some people hadn't written a lab report before, they hadn't written one in a long time or whatever. So now you all at least have a couple under your belt somewhere. So this quarter, the formatting and kind of what you need to include in the labs is going to be a little more strict. One thing that's different is, I know like with the radiometry labs, like you would go and do an experiment and it was very like formulaic and you get a result and it was like, this is or isn't what I expected. These labs are a little bit more like exploratory. You're going to have to do a little more research. You're going to have to figure some things out on your own, and then your results are going to kind of be like, you're going to have to evaluate them qualitatively or quantitatively. So there's the error analysis or, qualitative observations. This did turn out like I thought it should. It didn't. This is why. This is what it should have been. This is why it isn't what it should have been. So there's a lot more discussion involved. It's a lot, maybe a little bit less mathematical with the results and a lot more kind of qualitative, and you're looking at images and you're doing things like that. So personally, they're maybe a little more difficult to figure out sort of what you need to do, so you need to put a little more work in there, but they're a little more useful as well because it's stuff that directly applies to class and interesting things to figure out. It's a lot less step by step. So I would suggest getting started on them. And then, like I said, these are the guidelines. So this quarter, I'm going to have you follow like this format specifically. So there's 5 sections. There's up there like what you should put in each section. If you do a calculation or you generate a result and you put it in your lab report, it's just expected that you're going to discuss it. So you have to talk about it, have some observations and things like that. Don't just put like a plot or a table in there and just put it down and say like, these are my results. It's just, even if it's not in the handout, it's expected that you discuss everything that you generate. Like I said, because these labs are a lot more discussion and results based, just as opposed to like, I did this, this, and this, and I got this plot, and it's a number. It's a lot more variable between different students and stuff like that. So read through these, make sure you understand kind of what's in each section and stuff like that. Like I said, the biggest thing I want to emphasize is that the discussion is really, really important. That's the most important part of your lab report, because everybody's going to try to generate something, but in this case, a lot of times your results are all going to be different, or you're going to have done it a little bit differently or something like that. So please, please, please make sure you discuss your results. Put in all the equations you used, how you got to everything, and stuff like that. So a little bit more elaborate, but it should be a little bit easier to elaborate. I know, like I said, like with the radiometry labs, you get to a number and it'd be like, well, this is my number. That's what I expected. Sweet. So these ones, it should be a little bit easier, but please, please, please make sure you discuss the stuff that you put in your reports. And then there'll be a rubric with every handout too, so it'll show you kind of like what areas of discussion are most important. So look at the points. Yeah. Look at like look at the points, and see like, okay, this section's worth a lot of points, so obviously I should talk about it more. And yeah, so just basic, just like a few sections, but it kind of shows you like, so like this one, like the discussion of the heights and the errors, you should probably talk about like, were your errors what you expected? Like, were they bigger or were they smaller? How did they vary? How did you get the heights? Like just basic things like that. So just kind of check that out. Make sure you look at that. So yeah, it's going to take a little bit more thinking than the radiometry labs. I can guarantee that. Please try to think through them and kind of look at the book, try to figure it out for yourself. And then if you still have questions, come see me. I have office hours this quarter, so Tuesday, Thursday, 12 to 2, right after class. I don't know if that's gonna be bad if you burn out on the material and you're already here. But please try to come see me then. Unfortunately, I'm taking more classes this quarter, so I'm not gonna be. Last quarter I was around in my office a lot. If you popped in, I was probably gonna be there. But unfortunately, I won't be necessarily just sitting in there as much as possible, so, or as much as I was before. So if you come during that time, I'll definitely be there, and you can always send me an email too if you have any questions. Do you guys have any questions?
Are we going to discuss like in the class on the labs also? Or
Well,
after
whenever the photogrammetry equations today, right? So that's the baseline equations that you'll need in this one.
Though, I don't know, you probably talked about registration yet, right?
No.
Yeah, so this lab, like, I think you've talked about the photogrammetry equations. You can go back and find them in the book. The registration you probably haven't talked about, but just read through, like I said, the page numbers for all three of the things are in there. And so read through those and kind of look at it. There's just some like basic general equations that you want to probably include in your lab report. With the registration, Envy is going to actually do all the registration for you. So you don't have to, you never really have to use those equations. They're all under the hood, but you need to read through and understand it. And by your discussion of your results, it should show that you understand what Envy is doing and you know the interpolation method you chose and stuff like that.
So like I said, we'll do the registration in much more detail in the image processing class, and we'll look at all the underlying theory for it. Here, we just want you to learn to use it at this point.
So a quick thing about the images too for this lab, because this is like something stupid that probably took me a lot longer than I needed to figure out when I did it. The images are, so this is, what did you say?
Is that the one you want?
Yeah, so this is like the center image. Okay.
Come here.
Yeah, and that's the left.
Use that.
Okay, sorry. So this is the center image, and this is to the left, and then, so that's pair A. And then if you look at pair B, this is the center image. Did I do that right?
Yeah.
I think.
This is the center image and this is to the right. I just don't know which one to put. If you look at them side by side, you'll see one image is the same. So it's really like 3 images in a row. So you could line them up like 1, 2, 3 in a row, but then it would be a lot longer than your computer screen. Obviously, it'd be harder to zoom in and check them all out. So that's why they're split into 2. But you'll notice that one image is the same, and then there's one to the left and one to the right. So you're going to use the principal points in the 2 images to figure out the parallax. So when you look at the equations and stuff, that'll make more sense. But it really is like 3 images in a row. So if you look at the 2 images side by side, one is the same. And then the master image is just a larger version. So it has the whole scene. And you can see the letters there are of the different points. And I said this in the handout, but I should reiterate it again. I think like point A, it says like the right corner of the field. That could be any corner on that field. And it doesn't matter as long as you're consistent. So you could pick something different than the next person, different than the next person, but as long as you pick the same thing every time. So don't stress too much about like, oh man, what did she mean by the right corner of the field? Like, it doesn't matter. Just pick a corner and pick the same corner every time. The letters are just there to kind of give you a general idea of the area. And you're going to want to pick something that's easy to re-pick over and over again.
I don't know if anybody's ever been to the Syracuse University campus, but on that image, at the bottom, point C, that's the end zone of the football field. That used to be, that's what's the Carrier Dome right now. There's no dome on there. Just tells you how long ago this image was taken. And there's a lot of relief in this scene. Right? So it's a very hilly area. I went to grad school right next to the Carrier Dome there. It was the building I was in. And everything was a hill. It seemed like wherever you went, you were going upstairs for hundreds of feet. so it's a nice image to do this particular one.
Any other questions? And no late labs this quarter, because you're going to be talking about them in class. You're going to have a lot of other stuff to do anyway. You're not going to want to doing it. You're not going to want to be doing them later than it is. So just no late submissions.
How detailed do you want to talk about what we did in Envy? Like step by step what we did, or just kind of we co-registered them in Envy using this procedure?
Yeah, you don't have to say like step by step what you've looked at, and actually in the handout there's, it might be slightly different with different versions of Envy, but there's a little bit of a hint here on like where to click as far as what you're selecting. When you talk about what you did in Envy, the goal should be to try to explain that you understand what Envy is doing. So maybe reference the registration equations, you know, like how the interpolation method works and things like that. So it's going to do all the math for you. So yeah, rather than like I clicked this button and then I clicked this button, say like this step did this using this equation. So just kind of like, you know, it's you're just reading the book and doing it. So it's not, it's going to be a, you know, broad kind of overview or, you know, higher level understanding, not nitty gritty details, but try to reference those and explain what you're doing. Anything else?
Thank you.
Good luck.
And the due date's the same day as the first exam, which is important because there's probably going to be stuff like this on the exam. So make sure you get through this and understand the photogrammetry equation.
That's a screens exam question. Cool. Well, then we'll see you on Tuesday.
See you on that 4A exam.